All right, so let me welcome you all to the next edition of Mython AI Times. I'm really excited to see everyone who joined us in person and also online. My name is Tonda Hoskovec. I am the main organizer of Mython AI Times, and I wanted to introduce today's speaker, Dr. Suda from CIIRC, who leads the vampire group there. I'm gonna let him introduce the project. I wanted to mention a little bit of organization. The talk will be about 45 minutes, and there will be some opportunities to ask questions. If you want to ask a question and you are here in person, just raise your hand and I will hand you the microphone so that you can be heard online. And if you're online, please type your questions into chat. We will be monitoring it and I will ask the questions for you. With that, I'm gonna hand over to Dr. Suda to, yeah, the floor is yours.
Thank you very much, Tonda. Can you give me the slides?
I got to switch them.
I might be able to do it myself, but
no, I wanted to do it. I'm sorry.
Okay, so thank you, everybody. Thank you, everybody, for coming. The title of the talk is Vampire with a Neural Flair, and maybe because I think you've read the abstract, because that's why you're here, probably. If not, through the introduction, I'll try to explain what this all means. So let's jump directly in. It's going to be about automated theorem proving, which is my main research focus, the field of research that I'm active in, and it can be described as one of the classical disciplines of symbolic artificial intelligence. So we are here at AI Times, so that's probably a good address. Symbolic is also something that's called good old-fashioned AI, in contrast to what we see nowadays, mostly mentioned as AI based on neural networks, sub-symbolic, statistical, machine learning. So symbolic AI is at least as old, maybe older, I don't know, is based on logic, based on hardwired rules and symbols that we as humans can immediately interpret, unlike with neural networks where the representations that they are working with are kind of opaque based on vectors of real numbers, and the network decides on its own what it means. So we will be using in this talk, we will be using first-order logic as the language to describe the world. I'll have a little example or reminder. Of course, I cannot explain everything about first-order logic in 45 minutes, but I will try to put you on the right page. And what theorem proving does is it's kind of trying to mimic one of the most important activities that mathematicians do, which is using logical deduction to derive new theorems from what's already established. So we have some kind of certainty in this domain that what we learn is true by the rules of logic itself. And at the end, because it's proving, at the end we get a proof, which is some kind of artifact that we can look at and that we can inspect. We can get some understanding from it for why what was just shown to hold is actually true. So this is, again, in contrast with large language models, for instance, which can sometimes hallucinate. In automatic theorem proving, in the method itself, you have an assurance that, I mean, modulo bugs in the software, but they can always be eliminated. So in principle, the software is bug-free, right? And then at the end of the game, you have a proof, so you can even go and try to understand why what's been shown is true. And this field has some applications in math. Obviously, we are trying to mimic mathematicians, so we can also help mathematicians do their work. We can use automatic theorem provers to verify hardware and software, where verification, I mean formal verification, as opposed to testing, where with testing you can discover bugs, but with verification if you do things right, you can even like show that your software or the system that you are looking at is bug-free with respect to some specification that's written in logic. So this is how it all comes together. And I've been told that some participants of this meetup might be even using proof assistants such as Lean to do some formalizations in their own project. And automatic theorem provers can be used as little tools within these more complicated systems, which use typically more expressive logics than first order logic. And as a result of that, the problem is even harder and requires human attention. But the human is always happy if the simple things, the tedious things, can be, discharged quickly by some automation. So there is limits to what automation currently can do, but if it can be done, it should be better done by the machine than by the humans. And yeah, maybe so we have here the symbolic part, and the topic of the talk is how you can use the subsymbolic neural networks, reinforcement learning, to make this classical discipline or tools that come from this classical discipline, automatic theorem provers, even more performant by combining them, like marrying the symbolic with the subsymbolic, and getting something that's even faster and even more efficient. But back to logic. Just a little bit, a little bit of formalities, such that I have some vocabulary to use, and it's a little bit introduced. So the task of the automatic theorem prover is when it's given a set of axioms that are formulas in first order logic. Again, I'll have an example, and a conjecture, which is also a first order formula but has a different role. We are asking, does it necessarily follow that whenever these axiom holds, the conjecture also holds? And when the answer is yes, we would like to see a proof in some formal system. I will have an example of that, or I would like to illustrate what it means. But of course, the answer could also be no. And well, an algorithm, a polite algorithm would also answer no. But we are really with first order logic, we are really at the border of what's computable, what's achievable by algorithms in the first place. So even if we write a correct theorem prover, what can happen is that if the answer is no, it will run forever. And this cannot be avoided because of things like, computability theory, and it's related to the halting problem that you might have heard of before. But yes, we can deal with that. It's just that I wanted to highlight that the task is really hard. So our little examples of first order logic. So maybe you've heard of propositional logic at high school. What first order logic does to propositional logic with the well-known connectives of conjunction, disjunction, implication, equivalence. It's adding what's called quantifiers. This exists and for all. I could highlight them with the pointer. So this is the existential quantifier. This is a for all quantifier. And this formula you can find actually a Wikipedia entry about it. It's called the drinker paradox. And it's not actually a paradox per se, but it's a little bit funny when you read what it means in natural language. It says let's say in every bar or in every room, if it's non-empty, that's not stated, but it's implicit, there exists a person such that if that person drinks, then everybody drinks. And it's kind of paradox in natural language because it feels like that the person has the power to make everybody drink, right? But actually, well, I let you look it up if you're interested. Why is it not such a big deal, actually? But it's funny, and it introduces quantifiers. And then maybe you've heard of theologisms, like I think all the way back from Aristotle, and because we are with the Greek philosophers, let's talk about Socrates instead. And here's a little rule of inference. So this is like what the proof is in the end going to be composed of. Things like inferences like these. You can be saying like, if we assume that for every person, if that person is a man, then or every animal or every individual, if that is a man, then they are also mortal. And if we also assume that Socrates is mortal, then we can derive in one step that Socrates is if Socrates is a man, then Socrates is mortal. So this is really like the atomic steps. Such detailed steps are what the proof that we are after usually consists of. So it might be surprising that as I will claim, we can prove arbitrarily hard non-trivial theorems, and this is the answer. All the surprise gets kind of dissolved away if you realize that the proofs can be arbitrarily long. So it's not easy for the human to see, how you go from the beginning towards the end if there is 1,000 steps in between. But each of these steps will be as tiny as this trivial, relatively trivial syllogism. And to get an example of the whole theorem proving task that we might want to have solved, or mathematicians might be interested in solving if they didn't know it already. So if you are familiar with algebra, group theory, I have stated in the title, every group in which all elements are of order 2 is commutative. So on the left-hand side, you have a bunch of axioms of groups, associativity. There's something about the 1 is called a unit, right? And order 2 means that x times x is always 1. And on the right-hand side, you have the commutativity expressed in first-order logic. And in the middle, there is this logical entailment operator, which kind of the whole thing written down is like if every structure, every mathematical structure that satisfies the things on the left, if it also satisfies the things on the right. And the answer is yes. And I have a proof of this produced by Vampire that's coming in the next slide, but I've left it because it's kind of already like longish. It's left for the Q&A session if we have enough time and if there's interest. Okay, so what is Vampire? Vampire is the automatic theorem prover that I'm working on. It can be described as a state-of-the-art prover for first-order logic, but also beyond first-order logic, there are some extensions that we will not need today, but they are pretty fancy and cool. And in our field, we like to compete. This is how one of the ways, I mean, you publish scientific papers, but there is also this fun part where every year there is this theorem proving championship called CIIRC, and Vampire is kind of famous for often winning the competition. But it's not just my project. I actually joined the project that's kind of running since the 90s, thanks to Professor Andrei Voronkov, who's a professor in Manchester, and there are some other collaborators in Vienna and now also in Southampton, UK. Again, this is the outline of the remainder of the talk. I'll try to introduce some details about the technology that's behind Vampire, which is called saturation-based theorem proving, and about a particular moment in that algorithm that runs the prover, or that the prover is using to find the proof, which is called clause selection. Clause selection is kind of like a heuristic moment, which where the prover can decide kind of arbitrarily, but depending on the decisions, it either finds the proof quickly, or it finds it later, or it doesn't find it at all. And this is a perfect place where you can apply your machine learning. You can insert your neural network, try to train it somehow, and improve the performance of the system. So this way, we are kind of creating a neural symbolic architecture. Like the theorem prover is there for the symbolic, and the machine learning element is there to provide the intuitions to kind of fight the combinatorial explosion more quickly, because whole saturation is about search for the proof, search for the needle in a haystack. And if you have good guidance, then you are more likely to succeed than without it. And to achieve that, to train the neural network, I will introduce a little bit of reinforcement learning and how that kind of how I used it as an inspiration to derive the architecture. The architecture itself will be a topic of bullet point 3, and then I'll show you how perfect it works together and how it helps us prove more theorems at the end, hopefully, if we have time. So, just by the way, are there any questions so far? Okay, so some more technicalities that really you don't need to be afraid of them. We don't need to go deep, or for the whole story to make sense. You don't need to understand them in the finest detail. But I will try to introduce little elements of such that you kind of know or understand what the follow-up will be about. So saturation-based theorem proving in Vampire is refutational. What does it mean? It means that Vampire always seeks a proof by contradiction. And so basically, instead of working on this directly on this this relation somehow, trying to answer this question as it's stated, it immediately at the very beginning negates the conjecture and adds it on the left-hand side and asks, like, if I can derive a contradiction from this, then this is equivalent to entailing the conjecture from the axioms. So this is a first step. And before the search for the proof actually starts, we need some pre-processing, or we don't need it, but we do it because it simplifies many things later on. And part of this pre-processing is a transformation called clausification, where I'll sometimes mention, or maybe all the time, I'll be talking about clauses. So think of clauses as special kinds of first-order formulas that are of some specific form, simpler form than general formulas. Not so many propositional connectives are applied, and so on. It's kind of like an assembler of the theorem prover. So you just compile all the fluff away, and you are left with a bunch of clauses. I call them C1 to Cm. And they are kind of like working on this is equivalent as working on this, but it's kind of syntactically simpler. And the other ingredient that we need to have in order to run a prover is a logical calculus. That's the bunch of derivation rules which allow us to use to take what we already know, some of the clauses, let's say, and as premises. So this is like with the Socrates, with the syllogism, right? You have premises that are already known, and a calculus is a bunch of rules that tell you how to derive new stuff from the already known stuff. So, and this is the game that you play. You kind of apply the calculus as long as something new is arriving, and you are hoping to derive the empty clause, which is contradictory. You know, by definition, it's the unit of the proof by contradiction. And if you derive it, you are done. You have proven the original theorem, the original conjecture. And so it all boils down to combinatorial search for this empty clause in the whole space defined by the input and by the rules of the calculus. And saturation is just a fancy name for what I've just described, for systematically computing, you know, the closure, or like that's another fancy word, just, you know, computing, deriving the conclusions of the rules and adding them on a big pile, and until you've derived everything there is, or hopefully earlier you derive the empty clause and you are done. And saturation, in order to organize this process of computing the closure, what Vampire is using is called a given clause algorithm, where this is really just a bookkeeping device, how exactly to do this, such that you don't lose track, you don't forget to do something, and so on. And I have a picture about given clause algorithm that's coming next, so I will directly jump there. So basically, this doesn't even have to be logic, you know, for what I'll be talking about later. This could be really just round little things. For me, they are the clauses. But and this is all. The whole picture describes the pipeline, right? So you start with the input in some language whose strange names are put here, but you don't need to understand them. You parse it, you pre-process it, you create a bunch of clauses, and you put them. So, and there are these two sets that have been mentioned on the previous slides. One of them is called the passive set of clauses, and the other one is called the active set of clauses. Yes, please. So the question is whether the cone means something like in generative nets. I think it's not the same thing, or it's not. Well, when I was drawing it, I didn't have this connection in mind. There is a selection process. Basically, this is the whole thing, the clause selection heuristic that I'm going to describe, and that I want the neural network to govern, to decide what's the best next thing to take. This is kind of trying to highlight that the clauses are put into the passive container, and they are waiting there. And you always pick the best looking one, the most promising one, and you promote it from the passive set to the active set. We call this moment activation of the clause. And then, like at the beginning, everything is in passive. So at the beginning, the active set is empty. But as you keep adding things, the task, the invariant, the job that you are supposed to do is the selected clause comes into active, and there are some other clauses there. And sorry. It's in which one? So in passive, it's staying until you select it, and this is what you decide, which ones goes first and which ones goes next. And when you put it into the active set, then you inspect the rules of your calculus, and you are bound to derive all the clauses that arise as conclusions of the inference rules that the calculus has, where some of the the premises are in the active set. So because you've promised to do this all the time, so one of the premises is the currently new selected clause, the activated one, and then there is going to be a couple of rules with the clauses that we've already activated. That, you know, with this, this is kind of like this is how if we were to discuss the technicalities of the calculus, there is a resolution rule, there is a factoring rule, and so on. But we don't need to. There's just like logically precise prescriptions how you derive a new fact from the old ones. And then all the new facts go again into passive. And this is how you kind of make sure that you never forget about anything, because yeah, I mean, unless you make passive empty, you've still not finished your work. So this is like a kind of an infinite cycle that could run forever if the conjecture is not true. But if the conjecture is true, you will eventually derive the empty clause. This is guaranteed by some properties of the calculus. The calculus need to be strong enough. And when this happens, you are done. Okay, and so a little picture about why the clause selection heuristic is so important. So imagine that you put your input at the very top line, and these arrows are kind of highlighting the derivation rules, how they can give rise to new clauses from the old ones. And when we find the proof, this is the empty clause at the beginning, at the bottom. When we find the proof, what typically happens is that only a small part, even a small part of the input, but only a small part of what has already been done, all the clauses that we've produced, actually participate in the proof. So everything that's on the left from the orange part and on the right of the orange part corresponds to work that we could have also avoided and speed that we could have gained if we only knew upfront what the proof would look like. We don't. It's hard. Theorem proving is hard, as I said. It's only semi-decidable. But it also shows that there is a room for intuition and for heuristics that we would like to exploit. And so I have a slide about how clause selection has been done in Vampire since ages. And let's summarize the slide by just saying that there are pretty simple criteria about how you could select clauses, and these work reasonably well. I mean, before we come with neural networks and try to be smarter. And there is also this picture that could correspond to a nice, 5-minute story, and we cannot afford that 5 minutes right now. But if you want, I can tell you about it later. So let's jump into reinforcement learning. Why should we try reinforcement learning? Well, first of all, because it's cool. I don't know. Maybe you've been also following the news in the last more than 10 years now, but there have been some inspiring successes of, in particular, deep reinforcement learning. And my two examples are, I think, both from DeepMind. So this is a little bit boring, but I'm sure that some other labs did some cool things with them as well. There was this deep reinforcement learning agent playing the Atari games, just from the raw pixels of the game, and having learned how to play these games basically just by trial and error, observing the game, how it evolves, and then trying, move up, move down, shoot, and getting reward. And there was also this very interesting achievement where a program that learned just from a self-play was able to beat grandmasters at the game of Go. So that was a little bit later, 2018. And yeah, so if we have such an interesting technology, why not try it on our own task to potentially make it better? Yeah, in general, one could say what is appealing, at least for me, about reinforcement learning is that, I mean, after you set it up, after you connect your system with the neural network and with the algorithm, you can kind of think of it that it's programming itself. The only input is the reward that you define, what is good for the agent to achieve, and then it kind of randomly explores and tries this and that, and kind of construct some kind of internal model, and uses that to in the end hopefully even optimally solve the given problem. And yeah, it could even be that it discovers something that we've been overlooking, right? I mean, with the example of Go, I think expert players were saying that the algorithm or the program was playing moves that at the beginning, they were definitely not from the textbook of Go, right? They looked weird, but then in retrospect they realized that they were good weird and not bad weird. But for humans, they were like, what? And so this is also exciting. What if it automatically discovers something that we could again like analyze and see? Yeah, wow, why didn't we think of that? Okay. Key reinforcement learning concept. So reinforcement learning works roughly as follows. So we have an agent, whatever that is, right? So it has something with the brain, and it can act in an environment. It acts. So the whole game is played in discrete time steps. So there's like kind of rounds to it, and in every round, the agent somehow picks an action. This action allows it to, somehow change the environment. The environment may or may not give the agent at that moment some reward. This is the only signal about how the agent eventually, discovers what's good and what's bad. And the agent is also observing the world. So the agent is actually a neural network, and the input of the neural network is some observation of the environment. So it doesn't have to be the complete description, but some subset of the description of the environment, what it sees somehow or what it senses. And then the network defined so-called a policy, which is like the protocol that says, like, if you see this, do that. If you see this, do that. If you see this, do that. And that's basically all there is. And then the rest is, of course, like lots of technical tricks, but conceptually, this is the whole picture. And conceptually, if we apply this picture to automated theorem proving, and in particular clause selection, the agent for us should be the clause selection heuristic, right? And I was talking about the active set and the passive set. The passive set was this funnel-shaped thing, and at every moment, the only thing that we should do is to pick one of the clauses in the passive set, the most promising one, the most, the best one, the most likely one to be part of the proof that we are looking for. We have also the state space, or of the environment, and the observation space. Here it gets a little bit tricky, because in principle you would want the agent to base its decision on everything. In principle, you want to make it as general as possible. But there is a competing need for it to be, at least a bit efficient. I didn't say that, but Vampire is, a very well-optimized program, and if you slow it down to 1/10 of processing speed, even if it's a bit smarter, it will not help. So you need to be fast with evaluation of the heuristic as well. And then there is another question: how you set up the reward. Intuitively, solving a problem is good, so you should give a reward. But solving a problem can take 1,000 steps or 10,000 steps, 10,000 decisions, some of which are, irrelevant, most of which are relevant, and some of which are good. So, I mean, ideally, you would want, the self-programming approach that I was advertising in the previous slide should just say, yes, it's 1 point for solving a problem, otherwise you get nothing. But this is super sparse. I mean, this is even like a notion in reinforcement learning. Sparse rewards are a problem. The algorithms don't learn very well if you have sparse rewards. So what should we do? Well, what did I do? I completely ditched the state. What it means? Well, obviously, the theorem prover is changing state as it's selecting clauses and performing inferences. But I decided that the agent will not have access to the state, and it should just say this clause is good in absolute terms, not any, not any proof planning ideas in like, let's do this first, and when it's done, then we do something else. No, it's just similarly to how the good old heuristics that I didn't describe in any detail work. I just assign a number, and this number stays with the clause forever. It's kind of like it's not what you have to do, but it's a kind of design principle that I was using. And this also means that value-based methods where the network is really designed to say, well, this state is good, this state is bad, and then you pick your action such that you go to states that are deemed good, they are out of question. But fortunately, there are also methods called policy gradient methods that directly optimize a policy, and these can work without the notion of a state, and so I picked those. And with the reward, like I was already saying, that sparse rewards are not very good for performance. So there is a hack, and in retrospect, this is a really like reasonable hack that you could think of. Basically, you let the prover run all the way to the end. If it doesn't find a proof, that's bad. You cannot learn from that. If it finds a proof, then you say, well, all the clauses that ended up in the proof that are the good clauses, and all the other ones were bad. And you can reward all the steps during the run that selected a clause that eventually ended up in the proof. And you can say, well, all the other ones you should have ignored. So this is a kind of very pragmatic approach. And now the slides are going to start looking technical, but actually, let's not focus on the on the squiggly letters and on the indices too much. And just saying that I want to learn from these successful experiences, from the runs of the prover, which eventually ended up finding the proof. And I just want to tell you what this whole game with reinforcement learning is going to be about. So we have a neural network that's used for classifying the clauses, or no, not classifying. That's already a term. It's going to assign each clause a number. And what is a neural network for us? Well, it's some black box defined by some learnable parameters. This is the typical game. And when you apply this network to a clause, it's not obvious how that's done, but I will tell you a little bit about that in the next section. You get some values of the clauses, right? And we want these experiences, these successes, to be able to help us to find even better network that we're going to be even more efficient at finding these proofs in the future. So you want to update these parameters, these theta numbers. That's the brain of the neural network, such that you are even better at this. And the standard way how you do this in policy gradient methods is that you define, so you get these numbers from your network. So this is a clause, this is your network with its parameters, and it produces a number for the clause. And then you are in a particular state where you have your set of passive clauses. This is the big P. And so you have, let's say, 100 clauses there with their numbers. And you just turn these numbers into a probability distribution of selecting each of those clauses. So imagine a big pie, like a big circle, right? Which has the area of 1. This is the whole probability space, and you just want those clauses to kind of split this circle of area 1 into little, what is it called, slices of the pie. And the better the clause, the larger the pie, the slice. So super good clause should be like half of the pie, and bad clauses should be just tiny fractions. But when you select the super good clause, it gets renormalized, or like this is actually an exponentiation function. So you are not doing anything too magical, and this is like a super standard in machine learning. So that's why it's giving even a name. So you have heard of the softmax function probably at this seminar. And so in principle, the policy is stochastic. So you should be tossing a coin every time you go and select your clause. But practically, what I'm doing is that I'm picking the clause with the largest value, and then the next one and the next one. And new clauses are arriving, so you need to keep the data structure sorted. But that's how it's done in practice. And then there's this nice theorem, which I was really surprised to find that this predates the deep learning era. It's been described and discovered by Williams already in '92, and it's about how you should, if you have such experiences. And you already know what you mean by what kind of reward you want to assign to your agent, how you should adapt your network to to be even better at doing at accruing the reward, right? Like getting as much reward as possible along its runs. And so this is a gradient operator, which is the bread and butter of training neural networks. And even though we are in reinforcement learning, it all kind of actually boils down to exactly the same formula that you do with multi-label classification. So a negative log likelihood, and you have functions in your favorite frameworks like PyTorch for doing just that. So once you know what you are doing, this is not too different from. It's actually almost not at all different from doing some other simple machine learning tasks. Yes, so these are technical details about how, if you have more than one trace, and if you have more than one moment in time, and if you have more than one clause that ends up in the proof, like this is some kind of fairness, like democratic voting. Everybody has the same voice in the particular way that I used. You could probably play with these formulas and get some edge by. But yeah, a little bit about the neural network. How are we with the time? How are we with the questions? Is it relatively digestible so far? So you have seen the picture with the two sets, active, passive, and the trace is if you run the whole algorithm from the beginning to end. So the trace kind of records what was happening at each moment, what was selected, and what could have been done, what should have been done, and you also record what ended up in the proof in the end, so you know what's good and what's bad. So it's basically just summarizing the history of the run such that you can learn from it. Yeah. Way back. If it was here, then. No. This is first order logic. This is some squiggles from a paper where I took the description of the calculus. Yeah, thank you for the question. Yeah. Yes, but yeah, these are like really tiny technical details that I didn't want to go into. So don't don't worry about them too much. Okay. As I mentioned already, the design of the neural network, of the particular architecture that I was using to assign these values to the clauses, you need to strike the like balance between what it can use to decide, how informed it is, what you allow it to see in some sense, and how fast it's going to be. So that's one thing. And the other thing, of course, I wanted to, given the limitations, I wanted to give it as much information as possible such that it would, decide in a smart way. So the architecture is a combination of graph neural networks, which are a particular graph neural network is run on the formula input to kind of digest it and to produce embeddings of the logical symbols and of the input clauses that are later used to, as kind of seeds of the second part, which are so-called recursive neural networks, which are very nicely fitting to the logical objects that we are dealing with, the clauses and their derivation tree, because as I was saying, like new clauses are always derived from old clauses by a certain inference rule, but also to their syntax tree, because after all, it's a logical formula, so it's a disjunction of things, and each thing is an atom, and it can have some kind of like little sub things that kind of are put together in a little syntactic tree. So like a parse tree, basically, if you're familiar with programming languages or something like that. And this is very favorable for performance, because you can share substructures, and you can use some caching such that it becomes like as efficient as possible. By the way, recursive neural networks, I mean, they are generalizations of recurrent neural networks, which are, where the recursion is really just a sequence. You start something and you just keep, whereas here you are building a tree. And the funny thing is that one of the first papers, I'm not sure, I'm not perfect knowledgeable about the history of neural networks, but yeah, with some hesitation, I would say the first paper on recursive neural networks was actually applying them to logic back in the 90s. So some cool connection there as well. And this is how it looks in a single picture. You have the graph neural network doing something at the beginning. So, and then you start the prover, and it's deriving new clauses, and there's these two trees that are kind of growing and helping the network to figure out whether it is good or bad. Okay, I have a little time for telling you how the experiments went. What does it mean to do experiments in this setting? So we have our competition, and I've already mentioned that. Well, you've already seen the TP-TP. This is for 1,000 problems for theorem provers, and it's a library of problems, and it's also a format for specifying the problems in first-order logic. And the library has been maintained by Professor Jeff Sutcliffe at the University of Miami for the last almost 30 years. And so it's grown into something where there's like roughly 20,000 problems that your theorem prover can try and succeed quickly, or they are challenging, or we use them as a benchmark because it's a very, very diverse collection. So it kind of corresponds to what a theorem prover could be exposed to in the future in some sense. It's a distribution from the machine learning perspective. And what we typically do is that we try to see if we have some idea for an improvement, like how many problems are being solved in a certain time limit, right? You run on the prover on every problem, let's say for 10 seconds, and some problems are solved and some problems are not. And then you have your improvement, and you want to compare the improved prover and the old prover. How do they compare in 10 seconds per problem? And so what I didn't stress so much, but if you do the reinforcement learning, you start from a baseline. The baseline is the good old-fashioned vampire without neural networks. Then you collect the successes. You train your network on that. Then you plug in the network instead of the good old-fashioned heuristic, and it solves more problems. But then you have more training data, so you can do this several rounds. And as you keep improving, you are getting more proofs, and so you can learn even more from those proofs. So this x-axis here is iterations in this abstract sense, like how many loops did I do of training, evaluating, and as you see, at least at the beginning, the performance goes going up. There are some variations. I don't want to it's probably not so important to explain the distinctions between the three lines, three colors, but the distinction between the dashed and solid is that the solid is the training performance, so it's how well it's behaving on problems that it's seeing in training. And I was using the typical thing of having a train test split of the training of the data set. So we see that on problems that you are not directly training on, you are not getting better as much, but still going up. So that's good. Then there is a scatter plot which basically highlights the fact that, I mean, it doesn't highlight it, but I want to tell you the story that it's actually still quite expensive to evaluate the network. So there is a slowdown. But because I'm claiming that it's also solving more problems, the slowdown is compensated by the fact that the heuristic is much smarter. So the bottom line is that it's solving the problems in much fewer iterations of the saturation loop. So it's really much more efficient. So it's thinking a lot, but then it's also very, very, very much more targeted in picking the good things. And as part of the experiments, I also ran a little different setting, which took our servers like almost 13 days to finish on many cores. But through that, which was using higher time limit, so really targeting hard problems, and I was able to solve problems that were not known to be solved by any prover before. So that was really interesting and also exciting. And there is one last plot that I'll also try to quickly explain in detail. There is, this is time, and this is cumulative number of problems that particular configuration of the prover can solve within that time. So we call this sometimes a cactus plot, don't ask me why. But these 3 lines that are relatively straight, this is the old vampire with some variation of strategies or configuration. So you can of course configure the prover in many ways, but you see that these are relatively close to one another. And then this is the performance of, let's say, the fairly evolved neural guarded vampire. First of all, you see that at the beginning it's solving much fewer problems than the old vampire, and that's because the neural networks needs time to even get loaded from the disk. So it's taking I'm using millions of instructions of as measured by the perf tool, but you can think of 0.3 million. So it's what is it? 1,000 million, so 1 billion. So it's a split of a second, let's say 1/3 of a second on modern CPUs. It takes to just load the model, but then it quickly starts outperforming the good old-fashioned vampire, because it's more effective at selecting the good clauses. And this was supposed to highlight also one fact. So I was mentioning some configurations. It doesn't matter for this talk which configurations, but at the point, this let's say this avatar architecture that corresponds to this jump from here to here, from the dashed green to the whatever blue one. At one point, this was like a major breakthrough in theorem proving that deserved a paper at a very reasonable conference, and it's still considered like one of the nice achievements in the field. And that was jump from here to here. And now with the neural networks, we see a jump from here to here. So it's definitely doing something interesting, and I definitely want to explore it more. But this is for now. This is the results from this year. To conclude, so there is a architecture for neural networks that kind of grow all over the theorem prover and allow it to evaluate clauses for clause selection very efficiently. This is combined with the idea inspired by reinforcement learning about how exactly you should train such network, and then it led to some nice improvements in performance of the vampire theorem prover. I have some open questions that we can discuss, but first of all, I want to thank you for your attention.
All right. Thank you very much for the amazing talk. Are there any questions?
I may ask just for the LM part, like the part of the augmentation for the undeterministic model, like which models are you using concretely?
So there is no. Did you mention LLMs?
Oh, you maybe that was just my misunderstanding.
No, so there is no LLMs involved. So there's
no LLMs involved.
This is really like pre-LLM neural networks. It's deep, but it's not so deep. It's it's like the model has like whatever 3 million parameters.
Okay. So
it's
not large. Just
no. It's small. It's
okay.
It would fit on a floppy disk, maybe on 2, 30 years ago.
And it's just a custom-made thing. It's nothing.
It's custom-made thing in PyTorch. You just combine
PyTorch,
matrices and just build your trees.
Okay.
Yeah.
Right. I'm gonna also repeat that if you have a question online, just type it into chat. And are there any more questions? Yes.
Thank you. Yeah, I have a question about, like you mentioned, for the reinforcement learning, right? As I understand it correctly, you need to have, let's say, easier problems for that to work, so you can build on that. Because, like, for the harder problems, you wouldn't get any feedback on the training environment.
That's correct.
Right?
Yeah.
All right. And so, one question about that, like, for like when you're actually solving some conjecture, like, do you always build from like fixed set of axioms, like easy ones, or do you already have like a database of previous proofs that they can build on, right? Like if you have only small subset of axioms, there are the very basic ones, and for every proof you have to kind of build on top of it.
Thank you for the question. I'll try to clarify. The way the library is constructed is that each entry in the library, each problem is is fixed, and it's either hard or easy. There are variations. Like if there is one mathematical problem, that could be split into many subproblems. Then the library could contain the subproblems and the full problem as well. But I evaluate them individually. So for me, like one little problem is a tick, is one percentage point or one little success, and so for reproducibility, these are fixed. But you are right that as you work on a theory, you kind of keep growing your mathematical knowledge. But in the game that we are playing here, this is not happening. You just have and of course it is a property that I'm using of the library, that it contains the easy problems and I can bootstrap from them. But on the yes, so it's like this is called curriculum learning. Sometimes if you have like it's good to have problems that go from easy to intermediate ones to the hard ones, such that you can start from something. And fortunately for me, the TPTP library contains a lot of easy problems that the network could bootstrap from. But even the randomly initialized network, I didn't mention that, even like the super stupid one that could be even shooting itself in the foot, solves some of these problems. So there are also super easy problems that you can solve even with without a brain, just because the saturation algorithms is there to save you. Even if you are doing stupid things, if you are doing random stupid things, you will eventually solve the easy problems, and that's where you start bootstrapping from. So that kind of explains why it works even without limits.
Right. I might have a follow-up question on that, because at one point you mentioned that the neural network learns from the simple heuristic solver.
Mm-hmm.
Have you considered learning from the other algorithms in the competition?
That's a good question. Well, the other solvers in the competition are using variants of this simple heuristic. But
right.
But yeah, so there is the distinction. Maybe it's even here. Sorry, too fast. So one of the distinctions between the green and the base, base. So the orange and the green, one of those starts from the randomly initialized network, and the one starts from the heuristic that's already built into Vampire. So you see, so I would say, so because learning from the heuristic that was already there is beneficial, even in the long run, even it doesn't catch up after several iterations. There is this gap that persists. So my conjecture is because it's generally better to have more proofs to learn from. But I don't know. This is hard to know. But it's good to learn from the relatively smart heuristic that we have, rather than to start completely from scratch. Even though starting completely from scratch goes up and beats the baseline. So the baseline is this is the performance of the single Vampire strategy that is the default strategy here.
Nice, thank you. All right, any other questions? Yeah.
Can you give some examples of mathematical problems that were really solved by machines?
Right, there are a few. It's not 1,000 problems like in the library, but there was a big success, for instance, in the 90s, so-called Robin's conjecture. It was about, let me say it correctly, so about Boolean algebras and how they could be axiomatized in a single axiom. So there was this complicated axiom, very long formula. Normally Boolean algebras have 8 axioms, and this is what people see and understand. And this was some kind of you can do tricks and write a single axiom. And Bill McCune, with his system called Prover 9, maybe, or some other system of his, was able to crack this problem before the mathematicians did. So that one of the successes. We have a colleague in recently retired, so maybe no longer in New Mexico, but definitely until recently affiliated with University of New Mexico. And he's working on loop theory and making some progress with automated theorem provers. There is a project called the AIM conjecture, but I'm not loop theorist, so whatever I say might be wrong from now on about loops. So it's a niche area, but nowadays, so maybe you've heard of Terence Tao's equational theorems project. So it was announced like a year ago. It's a fun project because what he's trying to do is, looking at, it's very similar actually to, sorry for the jumping. Some people use HTML for slides and then they don't have to do this. If they have a tree structure, I have to do this because I have a linear structure. Where was my formulas? Here. So very similar to this. Like imagine that you allow yourself to write all possible axioms like this, single binary operation and up to 4 variables. And you can repeat the variables and you can, do the bracketing any way you like, and you write all these axioms. It's like, and then you ask yourself, does this one imply that one? Does this one imply that one? This leads to like 20 million problems. And so since Terence Tao announced it, a lot of people jumped on it, and within a month or two, they had the whole table solved. But obviously 20,000 problems, many of them are trivial, of course. But some of them were corrected by Vampire, and the ones where the implication doesn't hold sometimes have finite models. Vampire can do that as well. And then there is like, a tiny fraction where the counterexample is only an infinite algebraic structure, and Vampire cannot do that currently. But so they were using Vampire and Lean, the proof assistant I mentioned. They were using those to kind of, complete the table. And now that's a data point for Terence Tao. And he's like, now let's have a look on this. Maybe we can learn something about the structure of algebras and so on. So these systems are being used, but it's still like a niche area, I would say, for the common mathematical practice.
Nice. So maybe one last question.
Yeah, thank you. And I would like to ask problems from which part of mathematics are most suitable for theorem provers? Is it limited just to problems from algebra, or is it able to solve even problems from other parts of mathematics?
So that's an interesting question. Thank you. So algebra is the prominent example. I think maybe it's because humans are easily lost, in those rewrite rules with complicated, bracketings of things. But in principle, everything is open. You can formalize geometry. You can formalize. You can do set theory and therefore do any math. But to be honest, once you write down the axioms of set theory to a theorem prover, it will choke on very simple things immediately. So that's sad. But people are working on this. We have. Even like social choice theory, we have category theory. Everything is possible in principle, but the examples that I've been mentioning show that if you want to, help mathematicians immediately now, I think algebra is abstract algebra is where it works the best or helps the best.
Nice, thank you. So let's thank Dr. Suda again.